Let's go ahead and find the power series representation of G from the power series representation for F. The first step is to figure out a path to get from F to G. The suggestion is with differentiation or integration. Let's start with a derivative and just see where we're at. So we're starting with F, and I'm going to rewrite F so that it's easier to differentiate. I could use quotient rule, but let's go ahead and just use the power rule in this form. So the derivative of F, we bring the -1 down, we will subtract 1 from the exponent, and we will multiply by the derivative of the base. And if we put this into a fractional form with no negative exponents, we will have this expression. Now when we look at that, our goal is to get to G. And to get to G, which is right above, what we notice is that the only difference is the -10. So what we're going to do is divide both sides by -10. So if we divide both sides by -10, we now have, on the right-hand side here, we now are going to have exactly G. So this gives us a template on how to get from F to G. If we take the power series for F, take its derivative, and then divide by -10, we will get the power series for G. So that's going to be our template. Now to do that, we first need the power series for F, and we need to recognize that F is a modified geometric series. So to find the power series for F, we are going to look down here and see that the difference is that we're going to replace the x up here with -5x squared. So up in this geometric series form, we want 1 minus a quantity. So down here, the quantity that comes after the minus sign, 1 minus a quantity, that quantity is -5x squared. So we're going to replace x with -5x squared. So this will be the power series for F. Let's go one more step. Let's simplify it. Let's keep the indexing simple. We'll just put a 0 there. We know that it means 0 to infinity. And we will have -5 raised to the k power multiplied by x to the 2k. So there's the power series for F. Let's differentiate it, because we saw that our template needed the derivative of F. So differentiating a power series is super straightforward. We just differentiate it term by term. -5 to the k, that's a constant. So that constant, the derivative of a constant, that constant's just going to ride down. We have a constant times the power of x. The constant just comes along. And then we have to differentiate the power of x using the power rule. So we bring the power down and subtract 1 from the exponent. And now let's think about the indexing here. So k normally started at 0 up there. But notice, if you plug in a 0 to this exponent, you're going to get an x to the -1, which is not a polynomial. That is not a power series. Power series must start with a constant and then x to the 1, x to the 2, x to the 3, etc. So k cannot be 0. The first k value that gives us a non-negative exponent is k equals 1. So in other words, when you differentiate up here, you can think of it like we lost a term, which is how differentiation of polynomials work. If you have x squared plus x plus 1 and you differentiate, you lose a term. And so this jumping of the index up 1 that's the effect, is that we've sort of lost a term. At any rate, we now have the power series representation for f prime. And if we look at our template down here, in order to get to G, we need to take the function f, take its derivative, and divide by negative 10. All right, so g will be, we've already taken the derivative, now we just need to divide by negative 10. And we're going to combine some constants here. Like we see this 2 here, that can factor out to the front. And when we divide by negative 10 down here, that's out in the front. So those combined constants, 2 divided by negative 10, will be negative 1/5. And then we have our series portion of this. K is starting at 1, going to infinity. And we have negative 5 to the k. If we wanted to, we could separate out the minus sign here so that we have a switch. We don't need to do that, though. We can just leave it like this. And then we're multiplying by k, and then we're multiplying by the power of x. So there is the power series representation for G. That is it. Now, interval of convergence. Power series is not complete without its interval of convergence. When you differentiate or integrate, you can lose or gain convergence at the endpoints. So what we need to know is the interval of convergence for f. Once we know that, and then we differentiate, we would have to test our endpoints. Now the power series for f came with substitution, with a composition. That's pretty easy to find this interval of convergence. We just substitute whatever we substituted in for x. We do the same thing with the interval of convergence. So we replaced x with negative 5x squared. So let's come down here. So we're going to put negative 5x squared in between 1 and negative 1. We will divide everything through by negative 5. When we divide by a negative, we are going to reverse the inequality symbol. Let's see, divided by a negative 5. Let's flip this around just so it's easier to read. We normally are reading in this direction. So that x squared is between negative 1/5 and 1/5. Now there's a couple of ways to get at this solution here, solving for x. The way I'm about to show you is probably not a way you'll see in a book, but I think it's legitimate. We could use a graphing technique, which would also work. We could say, hey, we want to graph, we want to know what x's are between, what x's generate y values between negative 1/5 and 1/5. And you can see that the x's that are going to correspond will be the square root of 1/5 and then minus the square root of 1/5. You can also think of it algebraically like this. The left-hand side here of this inequality, that is always true. So the solutions to that inequality and the solutions to this inequality are the same. If we want this is a compound inequality. We want x squared to be both less than 1/5 and greater than negative 1/5. Well, it's always true that it's greater than negative 1/5, no matter what, because this x is squared. So the solutions to this compound inequality really are the same as the solutions to this inequality. And at this stage, we can take the square root of both sides. And when we take the square root of the left, the square root of x squared is the absolute value of x. And then the square root of the right-hand side is 1 over square root 5. And so this leads us to the compound inequality minus 1 over root 5 is less than x is less than 1 over root 5. All right, well, we know that the radius of convergence is 1 over root 5. And we know that the endpoints for the interval of convergence are negative 1 over root 5 and 1 over root 5. So we know that our IOC will have these two endpoints, but we don't know whether they are included or whether they are excluded. So we now need to go to the series and plug those in, negative 1 over root 5 and 1 over root 5. And so we're going to look over here, and plug in x equals -1 over root 5. And we're going to plug in x equals +1 over root 5. So this multiplication by a constant does not change convergence. So it suffices to ignore it. We don't need to consider that constant multiplier. So the series over here, and we don't really care where it starts at, that doesn't affect convergence either. So we don't even need to put a subscript for the k. So we will have, I'm going to now pull that minus sign out, -1 to the k, 5 to the k, k, and then x is going to be -1 over root 5 raised to the 2k minus 1. So let's just simplify here. So we'll leave this front pair of factors, or these front factors, alone for a moment. Let's simplify this. The -1 will be to the 2k minus 1. And then inside this fraction in here, I'm going to write that as 5 to the -1/2. So 5 to the -1/2, and that's all raised to the 2k minus 1. Okay, so let's keep on simplifying. We have -1 to the power of k, -1 to the power of 2k minus 1. We add the powers. So 2k minus 1 plus k, that's 3k minus 1. And then we have the 5 to the k, we have the k, and over here, we are going to multiply the powers together. So we're going to have multiplication by 5 to the -k plus 1/2. We now have some more simplification that we can do. This exponent, 3k, is always odd. 3k is either odd or even. It's the same thing as 1k. So it's either odd or even. We don't need this extra 3, though, so we can just simplify this to k minus 1. You can leave it, but you can take out the 3 also. So notice that when k is, say k is 2, up here you get 6 minus 1, which is 5, which is odd, so it's negative. So if you plug in 2 down here, 2 minus 1 is 1, which is odd, so it stays negative. And if you check a bunch of values, you can see that these are actually equivalent. Now I'm going to put the k here, that's this k, and I'm going to combine the 5s. So it's 5 to the, we have to add exponents. So 5 to the k, 5 to the -k plus half, we add those exponents, the k's go away, and we get 5 to the 1/2, which is the square root of 5. Okay. Now, once again, that's a constant. That constant can come out to the front, and it does not affect the convergence or divergence of this series. Multiplying by a constant does nothing in terms of changing convergence or divergence. Inside here, we have -1 to the k minus 1 multiplied by k. This is an alternating series. And this alternating series will diverge because a sub k does not go to 0. For an alternating series, this is a sub k. A sub k for an alternating series does not include the switch. So this is alternating. As k moves up, it switches from positive to negative, positive to negative. This exponent's going from even to odd, etc. A sub k has a limit that is not 0. So this fails the divergence test. So, or maybe I should restate that. The divergence test shows that we have divergence because the limit of a sub k is not 0. And so a sub k is that. and the limit of that is infinity. This is not equal to 0. The divergence test concludes that this is going to diverge. Okay, so we have divergence at the left endpoint. So over here, we can put a parenthesis right there. Now we have to go through the test at the right endpoint. So the right endpoint is 1 over root 5. So we're going to replace the x with 1 over root 5. So let's go ahead and do that. Let's see, so we are going to have, for the second endpoint, we're going to have negative 1 to the k. So we're essentially plugging it in back up here. So we have the negative 1 to the k, we have the 5 to the k and the k. And then we have our x. So there is x. So it's going to be 1 over root 5 to the 2k minus 1. We have to decide if this converges or diverges. Okay. Well, let's deal with that stuff in the parentheses over there. These parts, let's just leave alone. The numerator is a 1. In the denominator, we have 5 to the half. So that's going to be 5 to the 1/2 times 2k is k. Negative 1 times 1/2 is going to be that. Now we have a power of k in both the numerator and in the denominator. So let's combine those. So we have negative 1 to the k, we have our k, and now let's combine the 5. So it's going to be 5 to the, looking at our exponents, we're going to subtract them. K minus k, so the k's are going to disappear. And minus 1/2 is positive 1/2, so that's a square root. So this series, we can rewrite. Oh, I forgot my switch. So we need our switch. And this is also an alternating series. And this alternating series, very similar to the one above it, this alternating series is going to diverge. And the question is why? For a very similar reason. If we look at a sub k is everything inside the summand except the switch. So here, the a sub k is also not going to have a limit of 0. Let's see, I dropped, oh, I see what I did. I factored out the root 5 right there, but the k is still there. So a sub k will have a limit that's not equal to 0. So as k goes to infinity, limit of a sub k is everything but the switch. The limit of a sub k is the limit of k as k goes to infinity. This is infinity. This is not equal to 0. So our conclusion is diverge. So that tells us that our IOC is that. A lot of work to figure out this IOC. So there is our IOC. And our power series is, wherever it is, right here. This is our power series for G. All right. Long problem.